And ready for section 4.13. Behavioral modeling represents digital circuits at a function and algorithmic level. Used to mainly describe sequential circuits, but can also be used to describe combinational circuits. Behavioral models execute one or more procedural statements when launched by a sensitivity mechanism, commonly called a sensitivity list, which monitors signals and launches execution of the behavioral description. Procedural statements are like those found in other programming languages, for example, assignments and statements which control the sequence execution, for example, for, loop, case, and if statements. This section considers the behavior modeling of combinational logic. Behavior model of sequential will be considered later. And the first thing I talk about is Verilog. And you got your always, begin, end, assign, always initial. Oh, yeah, I was looking for the example for Verilog before we looked at VHDL. So we got this over here. It's our module or decoder or 2x4 line decoder. Two to four line decoder. This might be it. Okay. So we've got our output from 0 to 3, D, and that corresponds with our D0, D1, D2, and D3. And we have the A, B, and enable, which corresponds with our A, B, and our enable. And here we do our begin. Now the always, they indicate over here. Verilog behavioral description is a hard word declared with the keyword always, followed by an optional event control expression. So that's what this always is from. And then our A, B enable, and then begin. And so we got our D0 right there, which is the exclamation there. That's our invert right here. And then we got not A and not B and not enable. And each one of these coming in here looks like it's gone through the inverter. Then we got D1, which is our exclamation in the front there. That again, that's the piece right there. And this should be not A, B, and not E. Not A, B, and not E. And D2, again, exclamation up in front, and then I should have A, not B, not E. A, not B, not E. and then our last one should be A, B, and not E. So A, B, and not E. So that shows the behavioral, an alternative way to define the 2 to 4 line decoder. The begin and end, block off the procedural assignment statements. Verilog has 2 types of assignment statements, continuous and procedural. We have seen the continuous assignments use the keyword assign and the equals operator. Procedural statements are those made within the scope of an always or initial procedural statement. Procedural statements may use the blocking assignment operator, the equals, or the non-blocking, less than equal, depending on whether the assignment represents sequential behavior or concurrent behavior. The event control in a procedural statement effectively specifies when associated statements will begin to execute, because it suspends execution of the procedural statement until one or more of the signals in the expression has the event. It says down here with non-blocking, less than or equal statements, the order in which statements assigning values to the bits of D are listed does not affect the outcome. So these are all independent of each other. Now we also got VHDL. In addition to concurrent signal assignment statements and instantiation of components, a VHDL process provides a third mechanism for describing concurrent behavior. A process is formed by the keyword process, accompanied by an optional sensitivity list, and followed by declarations, definitions that begin in process, block statements. VHDL processes execute concurrently with other process statements, concurrent signal assignment statements, and instantiated components. So for that same definition here, we have our entity described here. We have our D coming in, or D going out, I should say. That's out. 3 down to 0. Then A, B, and Able coming in. Then our architecture, that's our, think of it as your definition. Architecture is down here. And you see we've got less than or equal to again. And D0 is not A, not B, not E, and then not in front. D1, not A, I think I'd have an easier time understanding everything if they didn't have mistakes. You see something wrong with that? Notice over here, we got a exclamation out in front. Then we got a beginning parentheses and then a closing parentheses at the very end. Because this right here, this exclamation needs to affect everything. Down here, they wrote the first line right. You got your not here, and then you got a beginning parentheses. You got another beginning parentheses, but that's closed off with a not A. Not B has parentheses around it. The not enable has parentheses around it, and then you have a closing one at the end. So this beginning one right here is closed off by this closing one. Over here, well, they messed it up. They put the not out in front. That's good. That's a plus. But then they didn't put a beginning parentheses around that. So I don't see any way that actually work. This not right here would just apply to this not A here. So this would actually say A and B and not E. A and B and not E, which isn't what it should be. So there should be parentheses right there and parentheses here at the end. And there should be a parentheses here. And they put a closing one here. Wait a minute, maybe this one's right. Let's see. Around that, starting one there, starting one. Okay, this one's right. And let's see if I messed up. One beginning parentheses, two beginning parentheses. 1, 2. Okay, that was just the first one that messed up. This one's okay. I wrote the book. Let's see if this one, beginning, yeah, closing. Okay, so that one's okay also. Okay, so just that one mistake there. But anyway, it just goes through and defines that same concept as what we looked at with the Verilog, just it's a little bit more wordy. Now here's an HDL. 2-to-1 line multiplexer. Okay, here's the 2-to-1 line multiplexer. Two-to-one line multiplexer. Well, that's in their letters, but that doesn't really matter. So I'm not sure which one that's supposed to match up against, but we'll just take a look at it. So we have our M out, A, B, and select. And they define that the M out is your output. You have A, B, and your select coming in. The select is going to drive which path we take. And then we got the M out here. That are always If select is equal to 1, so you have this select coming in to a certain value, then our M out is going to be equal to A. Otherwise, our M out will be equal to B. If you've used an if else statement, then that's pretty obvious what that's doing. Now notice it says that down here the signal M out in the MUX 2x1 they must be of the reg data type because it is assigned value by a Verilog procedural assignment statement. Contrary to the wire data type, whereby the value of the target of the assignment may be continuously monitored and updated, a reg data type is not necessarily monitored and retains its value until a new value in simulation memory is assigned. Historically, a type name reg has been a source of confusion to designers to suggest that a reg type variable corresponds to a hardware register. It may, but not necessarily so. Okay, here's showing the implementation of a if statement with a VHDL. Okay. Here's our standard definition again. We got our M out, and then the standard logic goes with both of these. So we got our M out, we got our AB. And then we have our select coming in. So you have AB and your select coming in. Then our actually architecture behind it. Got our process, we got our if statement, if select is equal to 1, then M out is A, else M out is B. End if, in process, in behavior. This talks about the general syntax for the if statement and various VHDL. What you can do, you can have an if, then, end if. You can have the if, then, else, end if. You can have an if, then, else if many times, then, and then end if. So you can have multiple else ifs, just like you can in a regular programming language. Down here, the if Boolean expression, then this, else if, then this, else if, then this, else, then end if. So the else if means something specifically is being met, Boolean wise. Down here, this else means just if it's none of the above, it does this one. Now this is an example of a behavioral 4-to-1 line multiplexer. 4-to-1 line multiplexer. Let's see if there's a picture that goes along with this. There's a 4-to-1 line multiplexer. Almost matches. We got our definition here. We got our module output. Well, it's not quite the same. The output out here is Y. They got M out. Our input, we got N0, N1, N2, N3. And we do have an I0, I1, I2, and I3 coming in here. Notice we also have an S1 and S0. And that corresponds. What I saw it. There is select. Okay, so we got our always here. This is a case statement. So if select is equal to this, select is equal to that, select is equal to that, select is equal to that, then it'll do the appropriate line there. Now, I remember right from last time, the first number here tells how many bits there are. 2 bits, which would be 00, 01, 10, 11. The apostrophe B represents Boolean. And then the actual value is 00 here. So this is like an if statement. It's checking to see if select is equal to any of these. If it is, then it handles the appropriate one here. In this case, I would my output would be my 0. Here my output would be 1, 2, and 3. Okay. That doesn't match up the picture exactly, so I can't go any more than that in terms of the matching the two together. Maybe I can. I see it now. The 00 here is based upon the input. So for example, if I have 0 coming in, 0 coming in here, okay. 0's coming in here, being flipped, so it's a 1. So that's coming in as a 1 right there. This is coming in as a 0, that's being flipped, so it becomes a 1, so that's a 1. So that's 1, 1. And then the I sub 0 will dictate what it is. Because if it's a 1, 1 times 1 times 1 is 1, so it's the same as the I 0. If it's a 0, 0 times 1 is 0, so that means it's the I sub 0 dictates it. So that's what they mean on this when they say that if it's 0, 0, then the answer would be I and 0. The next one, 0, 1. Okay, so 0 coming up. Where's it coming up? It's right here. 0's there. Okay, I have it backwards. This should be 0 and this should be a 1. So 0 is coming in, that's going through there, becomes a 1, comes up here, goes there. And this is a 1, comes here, goes up like that, and that's a 1. So 1 and 1, and then whatever I1 is dictates what the answer will be. I2 is 1, 0. This is 1, this is 0. So 1's coming in here. It's right here. 1's coming there. 0's coming in here. Yeah, right there. Just flips it. That's a 1. Okay, so I see that. And I3, 1, 1. This is a 1 coming in. Oh, I'm looking around down here. Okay, so it's a 1 coming in there. It's a 1 coming in there. It's a 1 and 1, and whatever that gives you dictates it. Okay, so that's our definition using a case statement. Does that make sense on what that's doing? Okay. VHDL. Let's see. Behavioral description of the 4-channel multiplexer. Okay, I don't quite see the picture of it, but that's okay. So 4-channel multiplexer. Okay, the same definition as one above. Okay, I see. With the VHDL. This right here is being represented in Boolean. 0, 0, which is 0. 0, 1, which is 1. 1, 0, which is 2. 1, 1, which is 3. So they're putting the actual values here, 0 through 3. Just like up above, if it's equal to any of those, these are just being assigned automatically what they're equal to here. Same rationale we talked about above. I'll grab a drink. Okay. Let's just talk about a VHDL down here, the bottom of page 220, and equivalent to the following conditional statements: M out is equal to N0, N1, M2, and M3. Sample 410. Where is it? I'm sure where example 410 is. We'll look at the code. This is what's, and we saw this somewhere based upon what was entered, that these just pass straight through. So if you had IN 0, when it's 0, 0 for your select, then that's going to be passed straight through there. LN1 is going to be passed straight through. 2 and 3 will pass straight through. This is an alternative process using a selected assignment, selected signal assignment. We got our channel select A and B. Process, we got I0, I1, I2, I3, and channel select. With channel select, channel select 0, 0, 0, 1, 1, 0, and 1, then it's equal to those values. Now this is Verilog case, case X, case Z statement. The Verilog case construct has two important variations, case X and case Z. First, we'll treat as don't cares any bits of the case expression or the case item that have logic value of X or Z. The case Z construct treats as don't cares only logic value Z for the purpose of detecting the match between the case expression and the case item. And I think I see any code for, or a code example. Now here we got the VHDL case statement. Got our case expression is, then when, case choice underscore 1, you do this sequential statement 1. When it's case underscore choice 2, you do this sequential statement. And when it's 3, you do this one. Case statement requires that the case choice explicitly include all possible values in the case expression. If they're not listed, the others clause is required, shown here in square brackets as an option. So this is when the above isn't true. Null statement should be used. That is when others goes null. And then 414 is writing a simple test bench. Test bench is an HDL program that describes and applies stimulus to an HDL model of a circuit to test it and observe its response during simulation. Test benches can be quite complex and lengthy and take longer to develop than the design that is tested. You have to think of this as like trying all of your cases out. Think about this one, for example. All my test cases out. There's 2 possibilities here, 2 here, 2 here, 2 here, so forth, because these are zeros and ones. Well, there's 10 of them, so that's 2 to the 10th, whatever that gives you. Let's see. 2 power. That's 1,024 possibilities. Okay. Result of a good a test only as good as the test bench that's used to test it, the circuit. That is important to have your design right before you go on and start manufacturing and so forth. Obviously, I think I only saw one major recall of spectrum analyzers when I worked at IFR. The electrical engineers had designed something wrong on the machine, and that recall is military recall, and it probably was a year long because they'd have to get replacements out to them in the field. Because if they're using that for anything important out in maybe a combat area, you have to have them a replacement for the meantime. Yeah, that was a big mess up. Test bench may seem tedious and so forth, and why do I have to do it? But if you're going to that field, that's much better than recalling 100 spectrum analyzers and having to ship them back and so forth to actually fix a circuit. Verilog. In addition to employing the always statement, Verilog test benches use the initial statement to provide a stimulus to the circuit being tested. We use the term always statement loosely. Actually, always is a Verilog language construct specifying how the associate statement to execute, subject to the event control expression. The always statement executes repeatedly the loop. The initial statement executes only once. So this initial here means this executes once. You're going to begin. A equals 0, B is equal to 0, and then A is 1, then B, and then A is 0, and B is 1. The block is enclosed between the words begin and end. Block assignment statements within the block are processed sequentially, subject to the delay, control operator #. That's what this is referred to. This operator has effect to suspending the simulator until the associated time has lapsed. Then the simulator resumes operation. In reality, nothing suspended or turned off. The delay control operator affects the scheduling assignment created by the next assignment statement as though the simulator was suspended. Yeah, it's talking about how the values of A and B are changing. This shows you the interaction between test bench and Verilog design unit. And let me go grab something. Okay. Now we got some built-in system functions that go with these. They give you, starting on page 224, the $ display displays a one-time value of variable strings with an end-of-line return. $write, same as display, $display, but without going to the next line. Monitor, display variables whenever a value changes during a simulation run. Time, $time displays the simulation time, and $finish terminates the simulation. Let me show you an example down here. You get your $ display, and then %d, %little b, %little b. They tell you up here, little b is binary, little d is decimal, H is hex, and O is octal. That's not 0, that's O. Or you could use uppercase. Uppercase is the ones you want. This one. Okay. Example specifies a string enclosed in quotes, may look like this. Time A and B. I think the difference between these two is, I mean, because this displays a string enclosed in quotes also. This one just puts words with it, makes it a little bit more readable. I think they should have actually said another example that specifies a string enclosed in quotes may look like that statement. VHDL test bench is on bottom page 226. It's an entity architecture pair written specifically to apply stimulus signals to verify the functionality of a design. The entity of a test bench is self-contained, does not have inputs or outputs. The architecture of a test bench includes an instance of the design unit control or design unit under test, UT, and VHDL process statements that generate signals test design. Okay, so we have A and B again. Never select. Okay, so this is we're going through all of our brute force trying our cases. This is where A is 0 and B is 1. And this is where A is 1, B is 0. This is where select is 0, and this is where A is 0 and B is 1. So it's looping through all these possibilities. Oh, those are commented out. That would explain it. Okay, so time here is B0. Is we put a delay on these, but not for the first one. A is 0, B is 1, 1, 1, 0. One, 0, 1, 0. Let me look at that example. I'm looking at this. I'm not really understanding what it's doing. 2 to 1 line, 2 to 1 line multiplexer. That's example 4.6. Well, this is 2 to 1 multiplexer, 2 to 1 line multiplexer, which is what they're implying this is off of. Has A and B, M out and select. A and B, M out, or M out and then select. Says if we're at the start of the testing, time wise, and then it says select is equal to 1, A is 0, B is 1. A is 0, B is 1. So that's coming in there. 0 times anything is 0, so that drops away or goes usually 0, I should say. For this one, if I have 1 coming in there, and for S, if I have S is 1. 1 and 1's 1, so that comes out as there. So we got 0 and 1, which gives us 1. Let me draw that. Okay, that hopefully helped. Okay, select is equal to 1. So this is having a 1 come in down here. A is 0, B is 1. A. Let's say this is A, I guess. It's 1, or no, this is 0. This is 1. It says we should have out a 0 coming through. Well, this one's obvious. That's coming in there. So 0 and anything 0. So that's going down there. 1's coming in here. That's 1 coming in there. 1 and 1's 1. So that's coming in there. 0 or 1. Maybe I'm thinking of that wrong. Maybe the data flow you can't think of in terms of the actual circuit. Because what they're saying down here is they're saying out is 0. And I thought they're coming up with a different way to come up with that same result. I'm not seeing the same result. But if I just follow this, select as 1, so that's 1. If A is 0 and B is 1, then since this is 1 or true, then that gives us A, which is 0. For this one, select as 1. So it's right here. A is 1, B is 0, out is 1. That makes sense because if this is 1 and the answer is A, which is 1. 0, so 0 here. It says and A is 1 and B is 0. Or out will be 0 because that'll be the same as B. Okay, that makes sense. A is 0, B is equal to 1. And select a 0, which means I'll choose B, which is 1. So that's why I get out is equal to 1. Okay. Not sure how that actually compares to our diagram. So I thought at first maybe it'd give us the same values. But when I ran the values through it, it doesn't give you the same values. Still seems weird to give you the same different values. But, oh. Down bottom of page 228, talk about VHDL. Then we got another test bench. Our entity defined in our architecture here. Then our begin. Okay, so that's all our defining. And this is a more wordy way of doing this. Assign those values and then waiting however many micro milliseconds. Okay, logic simulation 4.15. Last section of this chapter. Okay, logic simulation provides a fast, accurate method of verifying the model of a combinational circuit is correct, creates a visual representation of the behavior of a digital circuit by computing and displaying logic values corresponding to electrical waveforms and physical hardware. Two types of verification, functional and timing. In functional verification, we study the logical operation of the circuit independently of physical timing delays of gates using so-called zero delay models, which ignore the propagation delay of physical gates. Timing verification studies a circuit's operation by including the effects of delays through gates. The process determines whether the specification for the operating speed of the circuit can be met. For example, it must determine that the clock frequency of a sequential circuit is not compromised by the propagation delay of signals from a source register passing through combinational logic before reaching a destination register. Timing verification is beyond the scope of this text. Okay, so this is going to give us A and B. So we have coming in here. Those are doing an and giving us C. And then that's going through an inverter and giving us D. So we got A and B. Then your A and B giving you C all together. D's the invert. A is 1, B is 0. I'm not seeing the gate delays on that. But okay, I guess I do see it 50 now. 0 to 10 right here is just this right here. So values just right here haven't moved at all. And that's where A is equal to X, B is equal to X, C is equal to X, D is equal to X. So they're haven't actually been set at that point for testing. Then 10 to 20. Let's see what it says. That'd be simple enough I could follow that, but okay. Figure 4.40 shows the output that waveforms are produced by an AND invert circuit having zero propagation delays when its input waveforms are shown. Shaded area denoted the X value of a signal. Those are X values. The event time list and its associated data structures show which signals have an event. It's convenient to display this relationship on a simulator time axis as depicted in the figure. At a given event time, the signal change list has been ordered to illustrate the causal relationships between the schedule changes. For example, at time simulation time of 20, change the speed B changes the change in signal C, which causes the change in signal D. That's just what they're showing here. At 20, it's causing B to be 1, C to be 1, D to be 0. The simulator suspends TSIM while it updates memory to assign values to B, detects need to schedule C, and changes C. When C changes, the simulator notes that D must change, schedules the change in D, and then changes D. All these actions occur at the same instance of time, simulator time equal 20. but they occur sequentially with respect to a single thread of activity in a host processor. I guess I see it. A is 1, B is 0, 1 and 0 is 0, so that's why C is 0, which then drives D, which is 1. Then A is still what it was, but B is now 1. So you got 1 and 1, which is 1, so C is 1, and the inverter changes D to 0. Then we switch A to 0, so 1 and 0 is 0. That's where the C gets 0, and then D goes to 1. Then I get to this piece right here. This point, B is 0 and A is 0, and they don't say anything about C and D. It could be that their timing they set up, it just never actually does that. It stops right here. That's the only thing I can figure on that. Okay, effects of propagation delay. Logic simulator must manage the scheduling event for all the signals and circuits that's being simulated. A realistic simulation takes into account the actual propagation delays of the physical circuit elements. Each logic device may have a propagation delay associated with its behavior. When propagation delays are included in the models, signal changes do not propagate instantaneously through the circuit. Similar uses delay times to schedule the placement events in the event list. They have the indicated propagation delay between time. Okay. So here we got a propagation delay of 3. This says, affected by the change. The logic waveform event lists are depicted below the waveforms. Note changes C occur 3 times units, after changes to A and B. Oh, okay, I see. I'm understanding the picture now. A and B are right here. And then three time units later, that's where C is getting changed. Because 1 and 0, 0. And D, which is 2 units later. So this right here is 13. This is 15. Then D's get set. So D is 1. Okay, so this. Not sure how they figure in this time lapse here, 15 and 20, but then B gets set, and then 3 time units later, C gets set, and A is still 1, B is 1, 1 and 1's 1, so that's why C is 1. And then 2 time units after that, D gets set, which says D is 0, which makes sense because that's the flip of C. Another 5 units have passed. So then A gets changed. So now A is 0, B is 1. Multiply them together, that gives you C is equal to 0. And this 1, we went that back through. For our output. Then down here, B is equal to 0. Again, they don't actually do C and D for this last one. Does that kind of make sense how that propagation delay works? Bits of it I don't get. Like they have, initially they have a delay of 10 time units before A and B get set. But I'm not seeing any indication of 10 time units anywhere here. And then they have a delay. I guess a delay is 10 time units in all these, 10 to 20, 20, 30, 30 to 40. Okay, so I guess I see the 5 there, why that'd be 5. But I'm not sure where the 10 comes from. And I don't understand why they don't do the last piece, unless it just actually ends at 40. And so that's why C and D never get set. Changes to C occurs 3 times after the changes to A and B. The signal of D changes 2 times after C. Thus, propagation delay affects the location event list on the simulator's time axis. Okay, here's another example. This is a Verilog. Let's see, the inputs are specified with a 3-bit reg vector. Vector D. That's down here. D0, D1, D2. Okay. This up here, which I assume is our definition. Don't see that there at all. Okay, so the outputs of the circuit F1, F2 are declared as type wire. Over there. So F1 and F2. Complement of F2 is named F2 underscore B. That's a common practice for designating the complement. Must be missing something. I don't see F2B. Procedure follows step represented by figure 4.37. Which is right here. Okay. Input ABC, output F1, F2. Got our wires. Oh, there it is. F2 underscore B. Okay, so we got an OR ABC. Wish I had a picture of this, but I guess I was going to read it because I can't refer to a picture. Anyway, I got A, B, and C, and that's giving you the wire T1. These are ORs between them. Here's ANDs, A, B, and C. That's giving you G2. And then going to have all these breakdowns down here. Down here, defining reg 2:0 D, and wires are F1 and F2. And up here we got our begin, and then we got a 3-bit binary 000, and repeat, adding one binary each time. The next time it'll be 001, then 010, then 011, then 100, and so on. And that's what they're showing here. You're adding the 1 in terms of binary over and over. Nothing exciting there, they're showing you the output. Need a little bit more if we could verify to get to the diagram, but and then VHDL. Logic simulation of full adder circuit. First declares the components that will compose the circuit. So we've got an OR gate, and 2, and 3, not. Oh, this is there. This isn't the one above it. This is for the full adder circuit in figure 4.2. Okay, so that's over here on page 150. And so gate G1, OR gate, T1 is the name of the wire. Bring in A, B, and C. Okay. So A, B, and C are giving you T1. The AND 3 gate is going to give us T2, A and B and C. Okay. The G3, A and B. Okay, and B. A and C is G4. Yeah. G5 should be A and B. B and C. That's right, it is B and C. And F2 is going to give us E1, E2, and E3. I don't have them labeled over there, but I see what you're doing. It's coming from this over here into the G6. G7 is simply a NOT gate. F2. Okay. F2 is right here. No, that was off this order. Never mind. F2. Okay, yeah. The F2 is coming up here, and that's our not F2. Okay, that makes sense. And T3. Land. And gate. T1 and F2. F2B. So they brought it T1. Okay, let's see that. The OR gate. We'll bring in T2 and T3, and that's give us F1. Okay, so that's our definition of that. Now, at this point, we're going to have a looping construct to go through all of our possibilities. The variable they're using for the looping has nothing to do with the structure. I was wondering how they're going to do that. They're just looping through. K is going to 0 to 7. And then it just keeps adding 0, 0, 1 over and over. And that covers all of your possibilities coming in for your A, B, and C. Questions on test benches? Any questions on test bench? Right. Yeah. Not just. Oh, do you? Yeah. We're ready for chapter 5, but I don't think we'll start on it today. We only got 14 minutes left. So we'll start on that on Wednesday. And I'll get chapter 4 test out there. If you're still working on some of the past tests, you're not alone. So there's still time for the semester to finish all that up. Just don't wait too much longer. Get all those whipped out. I'll go ahead and stop the recording there.